in 3 dimensions, there are 2 coordinate systems that extend polar coordinates from 2D space into 3D space, and which can make solving certain types of problems a lot easier. So these are cylindrical coordinates, r, theta, z, and spherical coordinates, rho, theta, phi. So let me start out with cylindrical coordinates. So if our axes are x, y, and z, the rectangular coordinates, then for cylindrical coordinates, we try to locate a point in space by drawing cylinders of various radii centered at the origin, and we locate our point on one of these cylinders. So here r and theta are the same r and theta from polar coordinates. Or so another way of saying this is we use polar coordinates for the xy plane, and then the z is we just add on the z coordinate. So the formulas are x equals r cos theta, y equals r sine theta, and then just z is equal to z. And then in the other direction, we have r is equal to square root x squared plus y squared. Tan of theta is y over x, and z is z. One brief comment I'll make is, so this you might want to rewrite as theta equals tan inverse y over x. But this actually won't work because this can't tell the difference between x comma y and negative x comma negative y, since negative y over negative x is equal to y over x. So this relation is mathematically useful for working with these, but if you want to recover theta, you can't actually do it just from y over x. So in computer programming, there are functions math.atan, which calculates atan, like tan inverse, but there's also a function math.atan2. So if you tried to calculate, so math.atan takes in one number, and you would try to pass it y over x. As I just said, that doesn't work. Math.atan2 takes in 2 numbers, and so if you want to go, so you pass in the y and x numbers separately. So if you want to go from x, y, and find theta, then in programming you need to use this function to correctly get the quadrant, rather than just atan of the slope. Okay, that was just a little aside. So now let me talk about spherical coordinates. Okay, so these are rho, theta, phi. So in spherical coordinates, we sort of draw spheres of different radii centered at the origin, and we place our point on one of these spheres. So rho is the radius of the sphere. So the formulas are rho is equal to square root x squared plus y squared plus z squared, whereas r was only for x and y. Then we have 2 angles. Maybe I'll draw this as, so if our point is up here, theta is an angle in the xy plane, so it's the same theta as before. So we'll have, again, the relation tan theta is y over x. But then this phi will be, phi is the angle that it makes with the z-axis, or the positive z-axis. So theta goes from 0 to 2 pi, whereas phi goes from 0, which is up in the z direction, to pi, which would be down in the z direction. And so, for instance, pi over 2 is the xy plane. So to derive the conversion formulas, let's first just work in the xy plane. So if we had z equals 0, we would have x equals rho cos theta and y equals rho sine theta. And again, here, if we're in the xy plane, then rho will be equal to r. So in the xy plane, we'd have some theta, but then when we take into account the z-axis, so then we'll have so if this is our point, and this is the angle, and phi is the angle it's making with the z-axis, then we can see that, so sine phi over here and cos phi over here. So the height, once we put the radius in, so z, or once we put phi in, will be rho cos phi, and then this this phi. So if we imagine putting first the theta and rho coordinates, getting those correct, then adding the phi, when we sort of rotate up in the phi direction, we'll be moving backwards along this sort of vector and putting it over here. So now the new radius, the radius in the xy plane, instead of being rho, the radius from here to here will be rho sine of phi. Yeah, this is like the shadow of this guy moving over top. So our formulas become rho cos theta sine phi, rho sine theta sine phi, and then the phi we can get as phi is cos inverse of z over rho, or so z over x squared plus y squared plus z squared. And here we don't have that issue with the ambiguity because we're only evaluating cos inverse from 0 to pi, and it never takes on the same value for two of the same things in that domain. So I'll give in a second a demo. You can experiment which will probably make these easier to understand. Let me just give you the formulas for the volume differentials in each of these coordinate systems. And I'll explain these in the third video of this unit. So dv, we already know, is dx, dy, dz. Then in polar coordinates, dx, dy, we've already seen is r dr d theta. So the volume differential in cylindrical coordinates is dz r dr d theta. And you could write that in any order. So you could also write that as just r dz dr d theta, and yeah, many different. We can take the integration in sort of whatever order is most convenient. So you could move these around. So the new one is new piece of information is going to be the volume differential in spherical coordinates. So that will be rho squared sine phi d rho d theta d phi. So this is what I will sort of explain a way to get in video number 3. You could derive this by sort of a direct argument, as we did to find the volume differential or the area differential in polar coordinates. Maybe I should have said this is like dA is dx dy is r dr d theta. But I want to explain a more systematic way for figuring these out. So I'll do that in the last video. And then in the next video, I'll show just examples of working with this. Okay, so here then is the promised demo. So you can try changing the coordinates of the point in all these 3 different coordinate systems and see how it moves around. And you can also click on the boxes next to cylindrical or spherical to visualize sort of the shell that the point is moving along.